Firstly, just welcome to my presentation on infrastructure requirements to harvest woodlots in New Zealand and influencing factors. It's hoped that through quantifying infrastructure averages and finding out what drives them, industry will be benefited through using results as inputs to models and cost analyses, and by assisting in initial harvest planning, due diligence assessment, and cost reduction. Throughout this project, ArcGIS was used in conjunction with Google Earth to evaluate dependent infrastructure variables and independent influencing variables. An ArcGIS shapefile was provided by Baby Zoo, Bruce Manley, and along with the University of Canterbury that contained mapped woodlots throughout the 9 wood supply regions of New Zealand. This shapefile was used to sample 96 woodlots throughout the country. The 96 samples were split between the 9 wood supply regions of New Zealand using a weighted average. That's resulted in the number of samples in each region you can see on the board now. Each of these regional samples were then split between 3 size classes: 0 to 40 hectares, 40 to 99 hectares, 40 to 99 hectares, and 100 to 499 hectares. The percentages shown on screen now are the proportion of samples taken within each size class. Some literature defines a woodlot as up to 1,000 hectares. However, for the scope of this study, it's defined as up to 500 hectares. This was due to a couple of reasons. Firstly, there is a low number of recently harvested woodlots in the 500 to 1,000 hectare size class, and also by restricting the size, it limits the possibility of a range of extraction methods being used, which was one of the influencing variables being assessed. The image you can see here on the left-hand side of the screen shows the spread of the woodlots in the shapefile provided by UC, Bruce, and Vega. As you can see, the woodlots go right the way throughout New Zealand. On the right-hand side of the screen, you can see the sample of the 96 woodlots and the spread of them. This slide just outlines the infrastructure variables assessed, the dependent variables, along with the influencing variables assessed, the independent variables. Average slope, perimeter, and area were assessed using ArcGIS. Perimeter and area were both necessary for the boundary complexity calculation. The soil type was found using the online Landcare Research Soils Map, and the rest of the variables were assessed using Google Earth. As can be seen, the 3 infrastructure variables being assessed were road density, landing size, and landing service area. Originally, it was planned to use number of landings, the 3rd infrastructure variable. However, clearly this increases in woodlot size. Therefore, average landing service area was deemed to be more beneficial to industry, as it is in units of hectares per landing, and then this means that by dividing woodlot size through by this average, you should be able to get a rough number of landings required to harvest that woodlot. This slide just highlights the 2 main objectives for the study. So the first being to quantify average values for the dependent variables mentioned earlier. The second being to find out what drives these averages. The slide shows how the measurements were taken for each woodlot. So on the left-hand picture, we can see the landings are all outlined in blue. A landing was defined as any compacted, flat, contiguous area that had clearly been used as a landing. If roading ran through a landing, it was included in the area. If it ran alongside the landing, it was excluded. In the green, we can see the roading map for the woodlot. It was decided in the scope of this study to only assess internal roading. Therefore, any roading that ran into subsequent lots was excluded. That's why you can see the segment of roading up on the top left-hand corner disconnected from the main roading down the middle of the woodlot. A couple of exceptions to this rule were if the roading briefly ran outside the woodlot boundary for a switchback, or if the roading ran along the perimeter and was deemed to be a necessary construction to harvest the woodlot. So, for example, it wasn't part of a bigger road network. On the left-hand side of the screen, you can see the case where no internal roading was found for a woodlot. This occurred in 15 of the 96 woodlots total, and obviously resulted in a road density of 0 meters per hectare. Overall, these woodlots were generally very small in size. 14 out of 15 of them were less than 15 hectares in size, and then an overall average size of only 6.2 hectares. This slide just briefly shows how the average slope value for each woodlot was calculated. The image on the left of the screen shows an 8-meter DEM for the South Island. This DEM, along with the North Island one, were used to construct slope maps for both the North and South Island. The regional samples were then overlaid on their respective slope map, The zone of statistics, the table function was used to calculate the average slope within each of the woodlot boundaries. This example shows the South Island slope map with the Nelson Marlborough sample overlaid on it, and as you can see, these woodlots are outlined in black there. Here are the results for the infrastructure variables are displayed along with their 95% confidence interval. Two values are listed for road density. The first average shows the road density with the 15 0 metre per hectare values included. The second shows the road density with these values excluded. The road density value not including 0 metre per hectare values was used to assess the independent variables influence and was considered to be the more beneficial result to report. This is due to the 0 metre per hectare woodlot significantly lowering the average. Also, it should be determined early on in the harvest planning process if internal roading is going to be required on the woodlot. If this is the case, it makes more sense and will be more accurate to use the value that does not include a significant amount of 0 metre per hectare averages. Along with this, when making regional comparisons, the amount of 0 metre per hectare lots in each region will make a significant difference to the average for that region. The road density value of 29.9 metres per hectare appears to be higher than that mentioned by other literature, such as Chavez in 1965, which approximated density as 20 metres per hectare in early country. However, I did get in touch with Glenn Murphy, who zoomed in today, and he assessed 60 woodlots using a similar method and found the average for these woodlots to be 29.7 metres per hectare. Obviously, this is very close to the second value to see there, 29.9 metres per hectare, confirming these results. This et al. 2010 found landing size over a range of plantations to be 3,900 metres square. This study was done over a range of plantation sizes, and obviously this study was confined to small-scale woodlots. So 3,000 metres squared is about what we'd expect, considering we'll be confining landing size more. Literature around landing surface area in New Zealand was limited and difficult to find, so it does make this value difficult to compare. This slide shows the infrastructure averages by region. So the largest and smallest values for each infrastructure variable are highlighted in yellow. A NOVA test were conducted for each of the infrastructure variables. No statistical difference between regions was found for road density and landing size. However, surprisingly, a statistical difference was found between means for, regional means for landing surface area. To make any regional comparisons more reliable in the future, it would be useful for the study to be expanded and a greater number of samples be taken within each region. This would greatly increase our level of confidence and accuracy, as some of the regions did present a relatively low number of samples. Also, taking a greater number of samples within each region would increase our ability to compare regions against each other. This would help us find exactly where this difference in means for landing surface area lies, as in an ANOVA test if there is a difference, but does not state where the difference in means actually lies. Regression analyses were used to assess the influence of the 4 numerical independent variables. The 2 non-numerical independent variables, extraction method and soil type, were assessed using t-tests. These results will be discussed later on in the presentation. The chart shown on board shows which numerical variables had a significant influence, had a significant relationship with the infrastructure variables. The green squares highlight a significant relationship, and a number lists these from strongest significant relationship to weakest significant relationship, with one being the strongest. As can be seen, length-width ratio had the strongest relationship with road density, followed by average slope, followed by boundary complexity. Average slope had the greatest influence on landing size, followed by length-width ratio, followed by area, and boundary complexity had the greatest influence on landing surface area, followed by woodlot area. Length-width ratio was not expected to have as much influence on road density and landing size as it did. Its influence on road density is likely due to some very long woodlots, which had an entry point at the far end. This meant that roading had to be constructed right the way throughout the woodlot. You couple this with a very thin woodlot, you result in a small area, long the road, and a high road density correlating to a high length-width ratio. This differed to average slope, which was expected to influence the infrastructure variables and did have an influence on road density and landing size. Average slope having the strongest relationship with landing size is likely due to the fact that the landings were measured post-harvest. It's well known that contractors have a tendency to increase landing size throughout harvest if space allows. Much easier on a flat site as opposed to a steep site where earthworks are going. Extraction method was one of the variables that was expected to influence infrastructure means but did not. Although differences can be seen in the means displayed on board, no significant difference in means was found. Therefore, it was concluded that extraction method did not influence infrastructure variables. Along with conducting t-tests, box and whisker plots were developed to further show the spread of results. An example of this for landing size is shown on the board now. The rest can be found in my report. As you can see from this box and whisker, the maximum landing size for a ground-based extraction method greatly exceeded that for a hauler-based extraction method. Assessing soil type influence on infrastructure did prove difficult. The 96 woodlot samples were found to be located on 26 different soil types. This meant occurrences were very low for any given soil type, making any comparisons very weak and unreliable. Therefore, no significant difference in means were found. So soil type was deemed to not influence infrastructure. In hindsight, it would have been more useful to break these soils down into silt, sands, and clays, and then compare infrastructure variables due to the significant difference in workability between these three soil types. This obviously was not done in the scope of the study, but could be useful to do in the future. This slide summarizes the overall findings from the study. As mentioned earlier, it's hoped that these findings can assist industry in a variety of ways, including as inputs to models and cost analyses, assist with initial harvest planning, and due diligence assessment. Thank you for listening. I'll now take any questions.